Good day, everybody. There's a fairly simple guess or answer without doing much work to our question. We're looking for the smallest three-digit integer, positive integer, composite that is that satisfies this condition that the smallest prime is greater than the cube root of the integer. So you'll notice just by inspection, p is a prime number, is certainly greater than the cube root of p squared. All right. Now, put another way, if that gives you any trouble, just realize that this is equivalent to p cubed is greater than p squared, right? Again, p is a prime. So what does this say? It says we're looking for three-digit occurrences. Well, notice that let's see, I guess 7 squared doesn't meet the condition of 3 digits, right? But 11 squared, which is the prime after 7, is 3 digits. So just like that, we have a candidate answer. But we're not sure if we know it's an answer. We don't know that it's the smallest at this stage. So let's move along. Now this is what I just said right here, more or less. Yeah, this is just kind of the generalized notion of what we did up here. Now, this statement right here actually means that n cannot have more than 2 distinct primes. And let me just show you, if you don't, perhaps I don't need to show you that, but notice that p cubed would not be greater. Let's say n is 3 distinct primes, the product of 3 distinct primes with p the smallest, then p cubed is clearly not greater than p times q times r, where p, q, and r are all primes. Okay, I won't write that out, folks, but this is certainly true. So, in fact, and it takes a little more work to show this, any n that satisfies this constraint, and think of it's a fairly substantial constraint, the smallest prime has to be bigger than the third root of the number itself. So that's fairly restrictive, I guess, if you think about it a little bit. And so this has to be true right here. Notice that q couldn't be a composite number because that would violate this condition here. You would have at least 3 primes, right? So, and you can't do that with maintaining the minimality of p, okay? So anyway, now from this point on, we can create a list. Notice that this statement follows immediately from this statement. If you just take n to be pq, okay, take n to be pq, and you can treat inequalities more or less like equalities as long as everything's positive, Okay, so this statement implies this statement. So we need to have n such that p squared is greater than q. All right, so that's what we'll do. We'll compile a list. And that's exactly what I did right here. Notice that 2 times 5 can't be in the list here because 2 squared is not greater than 5. You see that thinking here, folks? We have to avoid that. Okay, 2 squared is not greater than 5, so we had to stop at 2 times 3. Now again, we're looking for elements in this list. And the similar sort of reason went through all the way here, like you can't have 11. 3 squared is greater than 7, but 3 squared is not greater than 11, right? And I'll stop just to avoid the clutter, but 3 squared is not greater than 11, so that's why 11 doesn't appear here. Now you just keep carrying on. None of these things, this list stops right here, so and none of these are 3-digit numbers, right? But on this list, notice that how all the squares appear, right? All the squares appear because p and q don't necessarily have to be distinct. All right, and so you get all the way up to 5 times 19 is the last 2-digit number, but 5 times 23 is a possibility, right? Because that's equal to a number that's less than 111. Is that 115 there? Yes, that's 115. And notice that we did find 121, which is a larger number, okay, than 115. And you see how you just keep carrying on and on and on in this fashion where you eliminate stuff and you maintain this 7, let's see here, 7 squared is greater than 17 by easily, right? And notice though that this is equal to a 3-digit number, namely 119. Okay, so you see we have these choices, 119, 115, and y'all notice how it's everything, all of these are, here's your 11 squared right here that occurred in our process. This would be 143, right? And you can see that the way you're going to construct this list, they're going to be numbers bigger than these numbers right here. So there's no need to continue this list, but none of the elements, the next list would start with 13 times what, 17 or something, and so you don't have to worry about those numbers being smaller than this number right here. Okay, so out of the numbers, let's see, we have, here's your 121 right here. Okay, I'll just put it so we have it on one screen. This is 121, which we were able to just figure out at the beginning. Okay, the smallest one of these is 115. Okay, and notice, well, we don't have to say anything else because everything else would be larger. Okay, so 115 is the element or the integer I got that satisfies the condition. 115. So I'll write that. What is it? I'm sorry, 215. My bad. No, 115. 5 times 23 is 115, right? Okay, so this is n's equal to 115. Cool problem, folks. I think this kind of stuff is fun. It's kind of abstract and computational combined, Okay, so that's our answer. And this part right here, I did a little bit of hand waving right here, but n has to be in this form. There's no other way because of this statement, which is crystal clear. And because if q wasn't a prime, you would still have 3 primes going on, and p being the smallest of them, right? So it's a pretty fun little problem. It came out of an Underwood Dudley number theory problem. He just asked you to prove that n over p was prime, which I just sort of glossed over, but hopefully what I said was convincing. All right, thanks for viewing.